of distributed.
Yeah, yeah.
That's
This
good.
is one of my project. Yeah.
That's very good. That's very good. So let's hear. So I guess we should start now, Isaac, shouldn't we?
Please, yes.
So good morning, everybody. Welcome to the International Association of Energy Economics International Online Conference. We have now the concurrent session 19, Photovoltaic. This time we will have 4 presentations. I will be the speakers. Well, myself, Santiago Arango, who is I am the chair of the conference of the session. Then we have Béla Figge, we have Jonas Sabelsberg, we have Amelie Sitzmann, Govinda Timilsina. So I hope you enjoyed and prepare your questions at the end. Each presenter will have 20 minutes, about 20 minutes for presentation, and then we will have about 10 minutes for Q&A. So perhaps we have a couple minutes less for each of you. So let's start now with the economics of distributed PV in Bangladesh, who will be presented by Govinda Timilsina from the World Bank, Washington.
Yeah.
So the floor is yours, Govinda.
Thank you, Santiago. Good morning, good afternoon, and good evening. So depending on where the audience are. Today, I'm presenting a study I recently completed on the economics of distributed photovoltaic in Bangladesh. For those who are not familiar with the photovoltaics, I mean the distributed PV, the distributed PV is basically PV photovoltaics, but it is installed in consumer premises and also connected to the grid, so that if there is a surplus electricity production, then they can sell to the grid. It is expected to benefit consumer through electricity bill reduction. It can benefit the utilities through supply cost reduction and transmission cost reduction. And it also benefits to the society as a whole because of the benefit to the consumers, to the producers, and also environmental benefits. However, the economics of DPP differ across the countries depending upon economic and technical characteristics of the DPP itself, as well as the characteristics of the electricity grids where the DPP is connected. So in this study, we evaluate the economics of DPP in Bangladesh from different perspectives. A perspective from owners or investors and DPP, perspective from electricity grid, and national perspective, and the perspective from the country as a whole. Our model accounts for the hourly electricity generation profile of the DPP, as well as hourly load profiles of the DPP owners and the grid. So I would like to show the methodology here, so how we have done this study. So through this flow diagram, on your left top, basically what we do, we assess the hourly electricity supply from DPP in different sectors. So basically it's not necessarily different sector because the hourly supply is the same for any sector depending on the size of the DPP. And then what we do, we match, we compare this hourly profile, supply profile with the hourly load and also the hourly load of the utilities. Then this comparison will show how much electricity produced from the DPP can be used by the DPP owners and how much it will be sold to the grid. Now, what happens on the consumer side, on the right-hand side, electric cost of electricity. So, what the consumer does, so they can reduce their electricity bill because now they're using their own electricity. At the same time, they can also generate some revenue because they are selling surplus electricity to the grid. But at the same time, so they have to pay for the installation of the DPV. So this is minus, this is plus, this is plus. So this gives what is the total gain or loss to the consumers. On the utility side, what happens is that so once the DPV offsets some of their sales, so their sales will be decreased. But at the same time, when the sales decreases, they also save the generation of the power, only the generation, not necessarily the plant. At the same time, they also save the losses in transmission and distribution system. Now, combining all together from the utility side and also consumer side, and also at the same time, since the solar, so there is environmental benefits. So we calculate here the benefit from the CO2 reduction. It gives the benefit to the society as a whole. So let's look at the data. So we start from the solar profiles, which is representative profile of the solar radiation in Bangladesh, because solar radiation can change from place to place. But since Bangladesh is not a very big country, and it does not change that much from one part of Bangladesh to the part of Bangladesh, but even then, so we use the solar profile from Dhaka as a representative solar profile. We can see so how this solar profile changes over the time in a day, from so basically start from 6 o'clock in the morning and it goes about 7 o'clock in the afternoon. But it changes, which season, which month of the year. So we can see here. So you can see the highest sometime in June, in July. So this is the solar profile. Then we have electricity load. So what we are trying to do, I can combine it, and produce one graph. But in the calculation, we have used the huge amount of data because these graphs represent every month. And even within the month, the load profile will changes whether it's the weekday or the weekend. So in this case, we have a 24 load profiles. So you can see, for example, here at the top. So then what we did, so what is the peak load and what fraction of the peak load, so represents in different time interval. So in this spectrum. So then what we did, there's some assumption, we assume that, again, we have an assumption we can change, whatever we like or whatever our particular project wants to do it. 3% of the 34 million households in Bangladesh, they have an electricity access, implement DPV. It could be 1%, it could be 5% or 10%, we could have any number here, but it's a 3% here. Each household provides about 11 square meter of space of DPV. It could change also. And one DPV has a 2 square meter in size, and it produces 0.25 kilowatt of electricity. And so combining all, so we have a total residential capacity of 1,371 megawatt. In the commercial and industrial sector, the commercial and industrial complex provide respectively 5.75 and 6 million square meter spaces for DPV. And again, we can change it. The size and rating of DPV is the same as before, like in the residential. The total installed capacity we consider here is 718 megawatt for commercial and 750 megawatt for the industrial sector. So for the data, so the capex, which is again coming from the IAEE, which is the International Renewable Energy Association, is the agency. So it's $840 per kilowatt for the residential DPV, 870 per kilowatt for the commercial, and 700 per kilowatt for the industrial. Again from IAEE. Utilization factor, since we accounted for the daily load curve, hourly load curve, so it is endogenous, we calculated based on the data. And so model also calculates the levelized cost of solar, which is $0.35, which is 3.5 cents, 4.1 cents, and 4.2 cents for the residential, commercial, and industrial consumers. On the other side, the electricity tariff, the current electricity tariff, because there is a time of day tariff in Bangladesh, and the tariff varies, across the season also, and across the type of consumers by voltage level. But the range is 9 cents to 13 cents. You can see the difference here, the cost of production from the DPV and the electricity tariff it presents. And that the transmission loss reported by the Bangladesh Power Development Board, BPDB, so which is which is about 3% transmission loss and 9% of the distribution loss, which looks a bit small, but still, that is what we got from the official source. Then what are the guidelines to pay DPV owners? The Ministry of Power, Energy and Natural Resources published the rule for net billing settlements in 2018. Distribution utility sends the customers, DPV owners, the electricity bill, accounting for electricity it receives from the DPV owner in each billing period. If the DPV owner is a net exporter of electricity, the net exports will be carried out over the next billing period. But at the end of the fiscal year, which is June, a DPV owner receives payment for the annual net sales using the utilities tariff for high voltage, 33 kilovolt, and which varies between 7.57 to 11.28 local currency per kilowatt hour. The DPP owners are obliged to pay demand charges and other fixed charges for all billing periods, even if they are net seller of electricity to the grid. Now let's go to the results. Basically, here it shows that how the load and DPP supply interacts. It depends on the size of the DPV. For example, on the left-hand side graph, so if the DPV capacity is twice as high as their peak load, then here we can see, so basically what happens is that they do not need electricity, the utility electricity between 9 to almost 9 a.m. to 3 p.m. Because they can produce enough electricity not only to meet their demand, but they also sell electricity to the grid. But if the size of the DPV is small, for example, in this case, if the size of the DPV is basically it is smaller, with 67% of the peak load, so in this case, so they will not be able to sell any electricity to the grid. They offset some part of their utility electricity, and if so normally what happens is that when DPP capacity is double of the peak load, DPP owners meet 37% of annual demand to own production and sell 30% of annual generation to the grid. Even if the DPP capacity is equal to the peak load, they can still meet 25% of the annual demand to their production, and they can sell 3% of the total generation to the grid. That is the advantage of the the mismatching of the load and the supply curve. So when the DPP capacity to the peak load is 0.67 or lower, a DPP owner do not have excess electricity to sell. Now, what is the impact of DPP to the consumer savings in the different tariffs? So we can see here is that if the current price is considered, current price offered by the utility, which is the price of the high voltage price. So in this case, this is the savings, it's the net savings of the consumers, or the net benefits to the consumers, which accounts for 25% of the total consumption, total utility bill. If there is no DPV by the residential sector, 29% by the commercial sector, and 34% by the industrial sector on average. So basically, the size of the benefits is about 30% of their total electricity bill. Now, if they use the utility sales price, which is a bit lower, the average price is a bit lower than the price, the utility pay for the DPP electricity, so it goes slightly down. So we can see it depends. I mean, it goes slightly down in the residential sector. It doesn't change that much on the industrial commercial sector, but it increases in the industrial sector because the utility sales price of the industry is already high, higher than the 33 kV. Now, the DPP cost is very low. If the utility say, well, we don't want to give you a high price, but we just cover your cost of production. So in this case, the benefit of consumers goes down, so compared to this section. And if there is also situation where utility say, well, so we don't want to pay any, any price to excess electricity, whether you give to us or you don't give to us, that's fine, but we can pay. So in this case, still, and they benefit because they save utility electricity because their production is cheaper than the utility electricity, and so this is the benefit, but it's much smaller than compared to other places. So now, as I mentioned before, the benefit depends on the size of the DPV with respect to the peak load. So the first graph is something, the peak load to installed capacity is half. That means the installed capacity twice as big as the peak load. So in this case, so this is what we already saw. But if the peak load is equal to the installed capacity, is still, they say, their saving is it's range from 12% to 19%, on average 15%. And even if they cannot sell any electricity, so they will still benefit from 6% to 10%. And so again, so we do some sensitivity. For example, if the capex is decreased and if the capex is increased, what happens if the capex increased? Obviously, the economics goes down, so the benefit goes down from 25% to 17%, 29 to 23%, and so on. And if the capex goes down, capex decreases, then the benefit also increases, and we can see from 25 to 32, and so on. So also we did a sensitivity on the which is basically discount rate, which we was in the main case 6%. Then we also consider 8% and 10%. Obviously, if the discount rate goes up, the benefit goes down from 25% to 40%, from 29% to 20% on average. So also another way to present this benefit is what about the benefit cost ratio? So
excuse me, Govinda, excuse me, you have 3 minutes left, please.
Okay, that's fine. That's fine. Okay, thank you. So if we see the benefit to cost ratio, we under the different sensitivity analysis, we can see in all cases the benefit to cost ratio is positive. In fact, it is twice as high as in the residential sector and almost 3 times in the 2.2 and 2.9% in the commercial and the industrial sector. So what happens to the utility? Now, because the utility, the main concern right now by the utility, so they are a bit reluctant to have a DPD because they think that they will lose their revenue. And then, so we try to say if that is the case. So their concern is valid as long as the DPD replaces the average electricity. The fuel cost of the electricity, average supply is 1.64 local currency per kilowatt hour. So that happens, it is replaced natural gas combined cycle, natural gas turbine, natural gas steam turbine, coal steam turbine. But Bangladesh uses a lot of fuel oil to produce electricity. So in this case, it's expensive. In this case, the utility saves a lot of fuel costs. So whether it's a fuel oil or diesel, so in this case, the utility gains, so it doesn't lose. So what happened to the, from the overall perspective, including carbon pricing, here we use the $40 per ton of CO2, which is the kind of shadow price of carbon used by the World Bank, the lower bound. So you can see here on all cases, depending what type of generation is replaced by the DPV, the benefit increases. For example, if it replaces the overall system on average, the benefit is 2.1% without carbon benefits, 3.6% with carbon benefits. On the other hand, if it replaces the marginal plant, which is the HFO, so heavy fuel oil, in this case, the benefit goes 13.6% to 15.8%, depending the carbon benefits. So, in conclusion, DPV system in Bangladesh are economically attractive to consumers in all sectors. The benefits are twice of the cost in the residential sector and higher in the commercial and industrial sector. The magnitude of consumer benefits are sensitive to input variables, including the relative size of the DPV, which is the load, electricity tariff, cost of electricity production from the DPV. The country benefits from the DPV, even if environmental benefits are not accounted for. The national gain depends on the type of grid electricity replaced by the DPV. National benefit increases further if environmental benefits are included. Impact on utility depends on the type of generation replaced by DPV. It will lose unless the DPV replaces fuel oil-based or diesel-based generation. Even if the DPV causes potential losses to the utilities, it should be promoted because of its overall benefit to the society. Let me stop here. Thank you very much.
Thank you, Govinda, for your presentation. I really enjoyed. So I have a couple of questions, although one of them you already answered, which I'm very happy for that. I open the floor. Some of the people might have questions to Govinda. Please go ahead. I think you can, you can just go and ask directly. We have some minutes for that. Well, while the people make up their minds, I have, I was going to ask you for the potential losses of the utilities, and I had it written before, but I am happy that you are. I have two questions left. One is, to what extent can it be expanded to other countries such as Colombia, the kind of a study you did? I would like to ask you for what is your perspective on that, and can you see any barrier that might be important for DPV, that might be important to point out here in this session, Govinda, please.
Thank you, Santiago. And this is a great question, how we can replicate this type of analysis in the other countries. The World Bank is very active to implement DPV in many countries. So, at present, we are replicating the same analysis in Tunisia, one of the North African country. So, similar analysis has been done for Turkey, I think Uzbekistan, Lebanon, many countries. I will double check whether some of our colleagues are still working in Colombia or not. If not, this could be something interesting. I can talk to them. Maybe we should also check the economics of DPV in Colombia. So that is something doable. Maybe we can communicate off the side and after sometimes on that. So the barriers, there is two types of barriers. So one barrier is that the utility is still, they have a kind of a reservation towards the DPV because they say that, look, we already, established the institution, we have the all the distribution facilities, there is a kind of economy of scale. Now, if you allow DPV too much, so in this case, we lose our business. They are always, reluctant. They are the main barrier to the DPV at present. But we are trying to, do kind of independent analysis and showing that, look, that may not necessarily be the case. It depends, so what type of generation is replaced by DPV. Now, I think Colombia, you have a lot of hydro, I guess, right? So in this case, maybe it could be also possible, DPV can.
Now we move into the next one, which is municipal building codes and the adoption of solar photovoltaics. Presented by Béla Figge from Georgia State University. Béla, please, the room is yours, so please go ahead.
All right. Let me just zoom.
That's great.
All right.
There we go, please.
Thank you. Okay. So, yeah, I'm Béla Figge. I'm a doctoral candidate at Georgia State University, and today I'm presenting municipal building codes and the adoption of solar photovoltaics. And this is joint work with Stefano Carattini at Georgia State, Alexander Gordan at NOAA, and Andreas Löschel at the University of Münster. So I'll just get right started with an introduction on solar photovoltaics and policy. So, of course, you know, as being here, we're aware of the reality of climate change and that the transition to renewable energy is important. And in many countries, of course, solar photovoltaics are a crucial element in this transition to renewable energy. And we also know that solar energy is approaching grid parity globally. So it's really has become a lot cheaper, and it has allowed thus for governments to phase out subsidy schemes. So as we've seen in the previous presentation, in Germany, the feed-in tariffs have been reduced substantially below the cost of production. And that, of course, means it's good in one sense, for sure, because these subsidy schemes are often expensive and regressive in terms of the distributional consequences. So, yeah, so we've seen these phase out of subsidy schemes both in the US and in Germany and in other countries. What we're getting at in this study is that there may be conflicting goals. So a hypothesis is that this goal of spurring renewable energy at a national level using subsidies and other means may conflict with other goals, particularly at the municipal level. And those may be, for example, the goal to preserve the aesthetics of an urban landscape or to preserve historical towns. So in practice, really, we hypothesize that there's a conflicting, that there are conflicting goals between national and local policy. Sorry, I'm scrolling here. So far, right, we see that economists have paid particular attention to how building codes help tackle climate change. So, for example, how they help spur energy savings. And what we want to look into is something that has not been considered so far, which is how building codes and municipal policy can actually slow the transition to renewable energy and hinder our efforts to fight climate change. So we connect to the existing literature in a number of ways. One, of course, there's the literature on the economics of solar adoption, which really has focused on financial constraints. And whereas here, right, we focus on constraints other than the pecuniary incentives. And then there's, of course, the literature on local versus federal policy at various levels, local public goods. That certainly plays a role here. And then there's a whole literature on the economics of building codes and their role in shaping urban environments. Of course, another point that's not listed here, but that is also relevant, is this idea of not in my own backyard, so NIMBYism. That's certainly also something that could play a role in what we're doing here, which is that municipalities may overall, support the overall goal of transition to renewable energy, but they prefer it if solar installations are constructed elsewhere and not on their own land. So just to bring that home, what we're doing here is we try to identify the trade-offs between policies aimed at defining the aesthetics of German municipalities and the adoption of solar photovoltaics. And we focus on Germany here because it is the country with the highest penetration, or one of the highest penetrations of solar photovoltaics. And there's also a high density of historical towns. So there are over 1,000 historical towns in Germany. So in that case, it's a very good case study for this sort of research question. And I give you a preview here of our results. We do find a reduction in the number of solar installations and capacity among municipalities that have implemented either permit requirements, so you have to obtain a permit to install solar panels, or have solar regulations of other nature. So I'll give you a little bit of background on solar energy in Germany. So what we have here is that solar is already about 9% of total production of electricity in Germany, with an installed capacity of almost 50 gigawatts. And as I mentioned before, the cost of solar electricity has reduced significantly and is now, when we compare to traditional fossil fuels, in the case of large-scale solar power plants, actually cheaper than the cheapest fossil fuel alternative. So you see here that lignite coal plants are actually, on average, at least more expensive than solar power plants. And even the small rooftop solar panels are competitive with many forms of fossil fuels. And that's what we're focusing on here, small rooftop solar panels that households would install. So in terms of the policy context here, Germany strives to increase renewable electricity production to 65% of total consumption by 2030. Currently, it's just over 50%. And solar, of course, plays an important role in reaching this goal. And one of the main policy instruments so far has been a federal feed-in tariff, as we just heard, which was actually implemented in 1991. But the feed-in tariff that was guaranteed was significantly below cost until 2000, when it was increased and considered a substantial subsidy. And since then, it's been continuously reduced and is now close to the production cost for small panels. And these are the feed-in tariffs for small rooftop solar. What we see overall is that prior to 2000, so prior to the substantial increase in the feed-in tariff, there was very little, almost zero solar capacity installed in Germany. And then we see this continuous increase over time. So that's important for our identification strategy, that there's very little solar installed capacity before 2000. So now to our municipal solar policies. So in Germany, municipalities have substantial regulatory agency beyond federal and state building codes. And it's actually the case that most of the land area in Germany, almost all available land, is administered by municipalities. So they do have a lot of relevant agency in this context. And just jumping ahead slightly here, we conducted a survey of German municipalities, and we found that almost a quarter indicated that they do regulate solar installations in some way. So they do use this power that they have. And what I focus on here is permit requirements and regulations pertaining to how solar panels can be installed on rooftops. So typical examples of how municipalities regulate the installation of solar panels is by specifying that they must be integrated into the roof, that they must be visible, that they cannot be visible from the street, right? That they cannot reflect light on other buildings or the street. So things like that, you know, it's really regulation to mitigate the impact that these solar panels may have on your neighbors or the overall aesthetics of the town. So I'll go right ahead to our study design, the survey we did, our matching and estimation strategy. So to obtain information on municipal policies in Germany, we contacted all municipalities in Germany using a survey, an online survey. So we contacted municipalities via email, and we really targeted individuals in municipal administrations that are responsible for implementing building codes, for writing them. So we really tried to get our survey to the experts that understand the sort of question. So it was really a survey designed for experts, and hopefully that allows us to get you know, correct, detailed information on what policies municipalities have implemented. And that took about a year. We started in late 2019 and finished collecting these responses at the end of last year. So yeah, I should mention here, I'm sorry, that in Germany, there are both independent municipalities and so-called collective municipalities that are just administrative unions of smaller, previously independent municipalities. So that's what we see here in bullet point 2 from this survey, which, you know, provides us with our treatment data. We have this data set on 985 independent municipalities, which is about 30% of all municipalities in Germany, and then 379 collective municipalities, which is also about 30% of the collective municipalities in Germany. So this survey provides us with information on when municipalities implemented solar policies. So this is a retroactive survey. So in the end, we have a panel from 1991 to 2020. So the key here is that we asked them to supply us with the documents and information on when a certain type of policy was implemented and if it was ever phased out at a certain point. So we construct a panel data set from this survey and the outcome data on the solar installations and the capacity from the Federal Network Agency. And in the presentation here, we really just use municipality level data, so the count of solar installations and the capacity installed at a municipal level. For other research questions within the scope of this project, we'll also look at the address level later on. And we also use some data on the municipality characteristics, so population data, the unemployment rate, and in particular the share of the Green Party in federal elections as well. So in terms of our empirical approach, the goal really is to compare municipalities that are similar, right? We want municipalities that have implemented solar policies that look similar to those that haven't, and to ensure that we implement propensity score matching on the municipality characteristics prior to 2000. So we match on the solar capacity and these control variables prior to 2000, and 2000 right here is the key, because prior to that there was very little installed capacity in Germany. We match up with onto up to 75 control municipalities with replacement, and that's really the idea here is to not lose observations. Given that only a small share, right, almost a quarter of municipalities in Germany have implemented solar policies, we would lose a lot if we only allow for a handful of matches. So we do that, but it doesn't really affect the results. It really just ensures that we can utilize our full sample size. So our empirical specification looks as follows. This is a generalized differences in difference strategy, or a two-way fixed effect model, depending on how you look at it. So our outcome here is the yearly flow of new solar in a municipality. So we measure the flow in this case. So either the number of installations or the newly installed capacity. And our main estimate of interest beta here is connected to the treatment, right? So it indicates whether a municipality has a permit requirement or implemented some other type of solar regulation. And then we have our time-varying controls, the same as in the matching strategy. We have municipality and year fixed effects. And then we have this matching weight. So we reweight the control municipalities based on our matching approach. So this estimate beta should be understood as the average difference between observed solar installations or the capacity in kilowatt per year in a municipality which has adopted a given solar policy, and a counterfactual estimate of the solar installations the municipality would have seen if they had not adopted the policy. Let me tell you what we find here. So the results for municipalities that have implemented permit requirements or regulations. So we have 4 columns here. We have always the log capacity in column 1 and 3, and the log installations in column 2 and 4. So we can think of the installations as the extensive margin, right? How many installations were installed, and then the capacity as the intensive margin. So each cell in this table is one of the beta estimates in the specification I showed. And this is panel data starting in
Béla, excuse me?
Yeah.
2 minutes, please.
Perfect.
Thank you.
Thank you. So, right, so the first row, right, gives us the overall effect. So this is on the total installed capacity and the total number of installations. And we see here that municipalities that have implemented permit requirements or regulations see a reduction in both the number of installations and capacity. So we should focus here on column 3 and 4, where we include the time-varying controls. And then what we do is we split it up by capacity percentiles. So in the other rows we see the effect for smaller installations. So 20 to the 20th to the 40th capacity percentile would be a typical household rooftop solar. The 20th percentile is around 5 kilowatt. And then for the largest installations, 80th percentile and over, that's more than 22 kilowatts. So too large for most rooftop solar installations. So what we see here is that most of the action in response to policy really is related to small rooftop solar installations. And this makes sense, right? Because large solar power plants would be located in rural parts of the municipality outside of, for example, a historical part of town. So they're not relevant and wouldn't really be affected by the regulations that we are studying. And what we also see is that the effect on capacity is larger than the effect on the installations. So that this would suggest perhaps that investors, homeowners are opting for smaller installations, right? For example, just on the roof that's not visible from the street. But they don't necessarily forgo solar altogether. And to give you a sense of the size of these estimates, this is in percentages. So about a 14% reduction in a given year in the number of installations in a municipality that has these types of policies.
Let's try to wrap up, please.
Yeah.
1 minute.
Yeah, sure. So in conclusion, right, so we find that solar photovoltaic regulations and these permit requirements have an impact on small and medium-sized installations, which confirms our hypothesized trade-off that confirms this hypothesis trade-off between national and local policies and goals. And in the case of Germany, right, we find that local policies make it harder to achieve national goals, but of course, they may be effective in other ways. For example, that they ensure the historical aesthetics of many German municipalities. Of course, some of these regulations that we've identified here may be getting obsolete in the current form as manufacturers are able to make solar installations less and less intrusive. And what we're currently working on is looking at policy effects within municipalities. So many municipalities actually only have policies in place for part of the municipality, for example, for the historical core of the municipality. So that's where we're headed. Yeah, thank you. I hope you have some questions for me.
Thank you, Béla. It was very nice to see your presentation and this new barrier that I didn't think about it, which is very interesting. Do any of you have any questions to Béla? Please go ahead.
Yeah, I have a question. I'm trying to understand, why these municipalities, having this type of adverse policies against the solar. What is the reason behind it?
Yeah, so the reason from a municipality perspective really would be to ensure that the urban landscape, right, the aesthetics of buildings is not modified. So in particular in Germany, there are more than 1,000 historical towns, and that these municipalities have an interest in preserving the way the buildings look. So they prevent homeowners from changing what they look like in order to preserve the aesthetics. And that really main incentive for that would be tourism, right? So that tourists still continue to visit historical towns and enjoy sort of the medieval, for example, medieval cityscape. That's sort of the driving mechanism that we hypothesize.
It seems there is also connection between your presentation and Amelie's earlier presentation. What Amelie is saying that, I mean, the solar installation is increasing, the residential solar installation is increasing, but what you are saying, is kind of decreasing. And I'm a little bit confused here, which way is the right way?
Well, so this, of course, the overall it's increasing, right? If we look at this graph, we're just saying that in municipalities that have these policies, like permit requirements, it's increasing at a slower rate. That's really what we're saying, and that we should think about the trade-off here, and that is it worthwhile to restrict solar at a municipal level, or should we, in the interest of mitigating climate change, make it easier for people to install solar panels.
I have
Any other question?
Yes. Thank you for your talk. It's very interesting to see other aspects of solar drivers. And I was just wondering if you have an possibility to control for the effects of the, I don't know if that's the English word for it, but we always talk about the tenant and the landlord like a dilemma in Germany. And I would suggest that in historical towns or in the in cities in general, you often have tenants, and this could reduce PV adoption, irrespective of the regulation in the city.
Yeah, that's a really good point.
I don't know if this is included in your fixed effects. Maybe they capture this effect. I don't know.
Yeah, no, that's something I'll have to think more about. We certainly can't explicitly look at that right now because we only have this municipality level data, right? We don't have building level information other than on the solar installations. But yeah, you're right. That's something we sort of had in the back of our mind, that would be an interesting direction to go towards. Sort of the different incentives that renters and landlords face. Yeah, very, very interesting. Difficult to address.
I guess we have data on this in Germany. So if you want, we can just chat afterwards or write an email.
Oh, you do? Okay, great. Yeah.
Thank you, Béla. I have one more question. I'm thinking about the. I've been always puzzled about how you have reached almost 30 gigawatts of installed capacity of this PV, while in other countries, I'm talking about Colombia, where I am now, we have. I mean, it's very little. It's really very little, and we have much more resources. Well, here we have all the Caribbean, all the Pacific, and we have. You know, all year long with a very nice power. But then I'm thinking about some of these new obstacles that you referred to about the especially historical towns where you might think about. I mean, of course it's a barrier, but maybe it's also that you might have a solution for that. Like you can think about when you have these towns, you can just, well, you can think about other alternatives such as like having the power plants a little bit outside of the towns. Have you thought about how to overcome these obstacles, or have you had some thoughts about that? That's very nice to see this new insight.
Yeah, that's a good point. So we haven't quite arrived yet at policy recommendations, really, but I think we see in the data what you're hinting at, right? That municipalities, you know, certainly are not regulating how solar power plants are installed outside of the town center. I think that's really where that could be offset, right? These municipalities could perhaps encourage solar fields outside of town. I think that would be a plausible alternative. Yeah. Well, thank you,
Béla. Yes. Well, you have got some very nice questions here, and let's now move into the last presentation. We have the market value of increased solar power production in winter, presented by Jonas Sabelsberg from CP at ETH Zurich. Please, Jonas, go ahead. You are mute, Jonas, please.
Okay, perfect. Thank you so much, Santiago. I want to get a t-shirt printed, with this "you're on mute" for my next Zoom session. Can you see the full screen slides? Yes, okay, perfect. Okay, thank you so much and for having me. It's a pleasure being here. What I'm presenting today is a collaboration with other people at the University of Basel, where I did my PhD, and at EPFL in Lausanne. So this is ongoing research, so we are happy for feedback, questions after the presentation. And Santiago said, the title of the presentation is "The Market Value of Increased Solar Power Production in Winter." And the picture you see on the slide is already a bit of a teaser of what I will be talking about. So moving right into the introduction, I think we've heard already quite a lot about this in this session, but just to briefly wrap up, basically, electricity will be really essential for decarbonization of the future energy system. So we have the Paris Agreement, basically following the Paris Agreement and the negotiations ongoing before that. We want to decarbonize, we want to achieve net zero emissions. And the electricity sector will really play a leading role in this whole decarbonization effort. This will be, on the one hand, basically due to the expansion of renewable generation capacities, replacing dirty old coal and even maybe gas power plant generators. And on the other hand, really think about electrification of other sectors as one of the key components of decarbonization of the entire system. Now, in this, solar PV generation is really expected to be one of the major drivers of global expansion. And this is due to several factors. And I think there was the latest IAEA report on this, showing that investment costs for solar PV panels have been falling rapidly. They're expected to decrease even further. And in many countries, solar power is now cheaper than coal or gas. And so this is something that has a big prospect for the future. However, we see certain issues with solar, as with all variable generation, basically, that at very high levels of solar generation, this mismatch between electricity demand and production within the day and also between seasons becomes more and more relevant. So within days, solar generation is usually highest during the middle of the day when the sun shines very bright, whereas demand peaks, at least in Western European countries, are often observed in the afternoon. We can address such daily variations by adjusting panel tilt to some extent, by implementing short-term storage options such as batteries or pumped storage hydropower. And additionally, even in countries that have their demand peaks during the day, where actually solar PV generation occurs when we really need it, increases in generation could exceed the demand peak and could even lead to a reverse in the daily profile. So for example, we know this famous picture of the duck curve in California. In addition to these daily mismatches, we also have seasonal mismatches between generation and demand. So for example, again, in Western Europe, we have pretty high demand in the cold and darker winter months. As you can see here, this is basically the entire NSOE region covering most of Europe, load being pretty high in the winter months, and solar generation, of course, being higher in the summer months. In this case, we probably need seasonal storage options, grid expansions, or additional wind power capacity to deal with this issue in a system with a very high level of solar generation. However, here we have the problem that the technical potential for seasonal storage or wind energy might be low in certain countries, and that also social acceptability of extending grid or generation capacities might be a problem. So for example, in Switzerland, we have basically zero wind generation, and there are very, very high burdens and barriers to adoption of wind power in Switzerland. So another solution that some people have come up with is basically placing solar PV in locations that have a different seasonal profile with a much higher level of winter production. And so this is basically another picture of what you've seen on the intro slide. And what we have here is a solar installation that's currently being built at the dam of one of the big storage lakes in Switzerland. And basically PV panels that are placed at higher elevations can take advantage of a number of factors. So we have a higher level of winter irradiance at higher altitudes. We have ground reflected radiation from snow. And we can basically utilize greater tilt angles to really improve winter yield, as you can see here in the placement of panels. And an additional factor that we have to take into account is that we basically have a higher efficiency of these PV panels through cooler panels from winds and lower ambient temperatures. So for example, this is also being implemented right now in a project in Portugal in the mountains close to the coast, where you basically utilize wind draft to cool the panels and increase their efficiency. And so this is something that some colleagues had been working on and had done some more technical studies. But of course, the big question is, do these placements and does basically using mountain solar really create additional value? And the other component in here that I will not be able to fully address is, of course, that you can expect such solar PV panels to be more expensive to build. But as I said, this is something where we have a lack of data on at the moment, and this is probably something for future research. Very briefly, a glimpse at what we find. So we find that placement in mountainous regions strongly increases market value of panel capacity due to increased winter production, pretty much across all different scenarios that we look at. And we also find that most locations with very high increases are really high altitudes in the alpine environment. So let me talk a little bit about how we found this. And as I said, we're taking a market value approach, and there has been extensive literature looking at the market value and cost of solar PV electricity production, or combined analysis of wind and solar, the pretty old Borenstein paper, some more recent papers on the German market by Leon Hirt, Josko paper on this. And what do I mean when I talk about market value? So market value is basically the generation weighted electricity price when PV is generating, compared to a base price, which is basically the generation weighted price over all hours, even those where solar PV is not generating. And here we can basically see that if we divide this market value by this base price, we can basically find the value factor of solar generation. So either we have a value factor higher than 1, so we basically have a solar premium. So solar is really generating in those hours where we have high prices, or it's lower, and then we basically have to consider a solar penalty. And for example, in this old Borenstein paper, we still have value factors between 1 and 1.2%. But what many studies have found, and what we also find, is that with increasing penetration, the market value actually declines, and this solar premium turns into a solar penalty. So for example, in Germany, the value of solar power has fallen from 133% of the average electricity price to about 98% as solar penetration increased from 0 to 4.7% and is expected to fall further in the future. And this loss in market value might potentially jeopardize the long-term competitiveness of solar power. So we have to think about approaches to basically increase this market value. And the other strand of literature really quickly is on technical potential of mountain solar installations. And these are 2 studies by our co-authors, Jérôme and Amelie, just for to briefly show them here. So what we will be looking at, or basically the starting point for what we will be looking at, is Switzerland as a case study for our approach. And Switzerland currently has the political target of replacing nuclear generation of about 25 terawatt hours per year by other generation. And so what we want to look at is a set of 3 different placement scenarios. So we have a business as usual placement scenario. We have an optimized scenario where we simply exclude mountain locations, so locations above 800 meters above sea level. And we have an optimized scenario where we include these mountain locations. So everything above 800 meters above sea level is also allowed for solar PV installations. And we combine these 3 PV placement scenarios with scenarios on the future development of the energy system based on energy trend assumptions for Europe. We combine this with different levels of CO2 prices And also basically to check for yearly variation in solar PV generation, we look at different weather years. So this is the underlying general logic. Full disclosure, we have not calculated all cross combinations here, but just included some of these as a bit of a sensitivity check. Just to show you the map. So this is Switzerland, and this is our business as usual placement. And you can basically see the panel area potential in different parts of Switzerland, mostly installed in the northwestern part and in the Ticino region. So the model framework that we're using, and since we're two different research groups, we had to combine two different models basically in an iterative process that is solved until we get a convergence between the two models. And the one model that we're using is the ORIS model, so more from the technical perspective, either looking at restricted, so no mountain areas are allowed, or at the full placement scenario where we also allow PV placement in mountain areas. To initialize the models, we use historical market prices, find a certain placement of PV, and then feed this into a big dispatch market model named SwissMod, a bit more on this in the next slide, and derive hourly market prices that then basically influence the PV placement that can be found by ORIS. And we loop through this process until we converge with the two different models. And then we can basically compare the market value outcomes for the two different models. And what ORIS does in addition is that based on an evolution strategy, we have an optimization layer that generates PV placement scenarios and really computes the spatially distributed production time series. And it also checks for technical feasibility, including grid constraints. And I think what's important to mention here is that we basically optimize on the market value of capacity. So we have a fixed amount of energy, as I said. So we have the 25 terawatt hours that we want to replace, and capacity installed is basically a free variable. Now, as I mentioned, SwissMod is a pretty standard classical electricity market dispatch model for those that are familiar with this approach. It's deterministic, assumes a perfect competitive market with perfect foresight, considers a whole year, but through different scenarios, we basically take into account uncertainty here. We have a detailed hydro and renewable generation structures within Switzerland. So what you see on this map is basically hydropower plants and storage lakes, and even the very tiny dashes here, interconnections between these lakes. And then what it really looks like is actually like a combination of storage lakes and power plants that are interconnected. So we really have a good grasp of how storage operates in such an interconnected system in Switzerland. And on top of that, we have aggregated generation structures for 19 European countries. So Switzerland plus neighbors and neighbors of neighbors. So in order to really take into account the very important effect that neighboring countries and developments in neighboring countries have on the Swiss electricity market. Now let's dive into the results. First off, just on the placement potential, what you see in the red colors, basically the PV area potential for the no mountain scenario, which is here. And then basically on top of that, we have the mountain locations included. So this is basically large parts of the Alps that can be included for mountain installations, with some regions, of course, excluded if they are natural reserves, for example, and parts of the Jura Mountains in the northwest of Switzerland. And as I mentioned in the introduction, and just to emphasize this point again, we can really see that there's a strong difference between alpine and non-alpine placements. And alpine placements are actually also better in summer, as you can see here in the dashed graphs. And this is for the 3 different weather years. And what we see is that the difference basically between alpine and non-alpine placement is especially striking in the winter months. Now, looking more at the market component in here, what we see is something that we probably expected, is that due to this mountain placement, so the green lines, and what you see here, it's basically the electricity price, average monthly electricity price for the 3 different CO2 price scenarios. for the weather year 2015. And we can see that the optimized placement in the mountains has a decreasing effect in winter on prices and a slightly increasing effect in summer in comparison to the business as usual scenario. And the optimized placement scenario without allowing placements in mountains above 800 meters above sea level lies somewhere in between. And what we can see here is that this effect basically holds throughout the different CO2 price scenarios that we take into account, even though, of course, differences between winter and summer prices get larger if we consider higher CO2 prices. Now, thinking really about the increases in market value that we can achieve, and this is now always in comparison to the base business as usual scenario for 3 different CO2 prices in 2025 for the 2025 electricity system and for the 2040 electricity system, assuming a very high CO2 price, we can see that the market value of capacity, so basically the market value divided by the capacity that we install, increases quite dramatically. So we see increases of about 20% in the mountain scenario, but even in the optimized no mountain scenario of about 8%. And all these results shown here are for the weather year of 2015. And but for the different weather year sensitivities, we observe quite similar patterns, and I'm going to leave them out for the sake of conciseness. And now the other interesting finding in here that the distribution of market value is strongly shifted, basically moving from the business as usual through the no mountain to the mountain scenario. And again, this is for the weather year 2015 under baseline CO2 prices and for the 2025 electricity system, but results are quite similar across CO2 price scenarios and electricity system scenarios. So what we see here on the one hand is that the distribution shifts to the right. The dashed line shows you the average market value of panel capacity in the scenario. And what you can see really is in the mountain scenarios, we get this really long tail on the right-hand side with a very strong increase. So this effect that I've shown on the last slide of a 20% increase in market value of capacity is even much more pronounced for a certain part of these locations. And these are mostly those that are very high up in the mountains. And basically, to sum it up, the statement here would be the higher we place them, the better. What we can see in addition, now here again for 2015, for the no mountain and mountain scenarios, that so what you see with the blue dashed lines in the background is basically areas where we're actually building solar PV in the no mountain scenario on the left, and then in the mountain scenario on the right. And we see that there's a bit of an overlap, especially in the Valais region, but also and the Rhone Valley basically, and in some parts of the Ticino. But then really a lot of different placement areas are being used. And this is mostly our alpine locations above 800 meters. Right?
Jonas, please,
yes.
2 minutes, please.
Yes, perfect. I'm almost there. And so what we see basically is that we are able to generate a targeted 25 terawatt hours with about 18 gigawatts peak generation in the business as usual scenario, whereas in the mountain scenario, we only need to install 15 gigawatts. So we can also quite strongly reduce the amount of capacity needed. Exactly, and I think the other important thing to say here is that driven by our market logic, really we push a lot of generation into the mountains. And so in this mountain scenario, we have about 80% of the generation in areas that are above 800 meters above sea level. Now let's move quickly into the discussion. So what we've done, we basically explored the effect of increased winter production on market value of PV panels under different scenarios. We show that placement in mountainous regions increases market value due to increased winter production across all of the scenarios we looked at. And we also show that basically across these scenarios, the level of increase is pretty constant. And we find that most locations with high increases are really in an alpine environment. And again, the statement, the higher, the better. As I mentioned in the introduction, a cost-benefit assessment in this regard is quite difficult to calculate due to the high heterogeneity of investment costs that we have due to difficulties with road access, proximity to existing electric infrastructure, project sizes, and so on, which will have a strong impact on investment cost per kilowatt. And so the picture I've shown in the intro is probably one of these low-hanging fruits with a pretty high yield. So we're really in this very high region, and we already have a good access since there's already a power plant built in this region. I think this is where we'll see most of the investments in the near future. So after 20 minutes, I'll conclude and thank you for your attention. And I'm very happy for any comments or questions.
Thank you, Jonas, for your presentation. And now we have some minutes to ask Jonas some questions. Please go ahead if you have any, please. Well, I have Jonas one question, just a little bit of a background question. It's about the pumped system. Have you thought about how to include the pumping stations that you have in Switzerland for your analysis? Any thoughts on that, please?
So, I mean, in the model that we're using, they're fully included. So this is already taken into account, the interaction with the electricity market in the end. What we have not yet looked at is how basically pumping behavior over the year is influenced by these different scenarios. But I mean, in the end, this is strongly driven by market prices. Yeah. And should follow a similar pattern as we have seen basically in this price graph for the different scenarios.
Yeah, I have one question, Jonah. Yeah.
Please go ahead.
Please go ahead.
My system is very slow here. Yeah, the question here is that you are talking about higher value in the winter because there is a lack of supply capacity. But at the same time, we are talking about higher value if we can produce in the mountain. But again, during the summertime, there might be no snow, and the production capacity would be lower in the summer, even in the mountain. So I don't know whether you have taken into the seasonality constraint into your model.
So I mean, from a technical perspective, I think we have taken all these things into account that you just mentioned. So really thinking about the strong level of seasonality, we take into account different weather years. We look at we take into account weather model data in this regard, and so the yields that I've shown already take into account differences in snow cover throughout the year, for example, differences in panel cooling due to temperature or wind. Does this answer your question, or am I going in the wrong direction here?
No, as long as if the model accounts for a monthly load dispatching, even seasonal load dispatching, and also the production profile, I hope you capture it. If the model does not go, with a seasonal production capacity, then maybe not.
No. I mean, the model that we're using, or both of the models that we're using, have an hourly resolution covering an entire year, so 8,760 hours that we're optimizing combined. And basically, the time linking is done through storage optimization in the end. Yeah,
so that is on both sides, right? Supply and demand side.
Yes, I mean we assume demand to be mostly fixed. So this is a cost minimization approach that we're taking, but we are fully optimizing the supply side. Sorry, I didn't go into more detail on the dispatch model, but that was just due to the time constraint that I didn't explain it in more detail.
Is there any more questions to Jonas?
I have one more question.
Yes, please,
Javier.
you looked at the market value, so the generation weighted electricity prices for solar. Have you also looked at the value factors, so the relationship between the solar market value and the evolution of general prices?
Yes.
So yeah.
Yes, absolutely. Let me just briefly share this slide. So there we go. Okay, so we have looked at the value factors, and what we find is that, of course, at this very high penetration rate, as I mentioned in the introduction, of 25 terawatt hours of solar PV production in Switzerland, which is about 40% of Swiss load, or covers 40% of present Swiss load, we have value factors strongly below 1. But at the same time, we are able to increase these value factors by a few points in these scenarios. And we have also looked at value factors for other countries in Europe of their solar PV generation. And we find that in this future electricity system, none of these countries achieve a value factor of 1 or above. I think apart from Spain, which slightly touches the 1. And but I think the important question here is, or the important point in here is that we assume the demand side to be rather inflexible. And if we have demand side participation in the system, also thinking, for example, about green hydrogen generation and so on, this might then shift this market value component again, if we basically increase demand in hours where we have a lot of solar PV generation.
Mm-hmm. Thank you. But as I see in the table that you are showing, the value factor actually increases with this strategy.
Yes.
So that's quite remarkable, right? Because it means that it doesn't only increase the market value of solar, but also its value with respect to the general value of electricity.
Absolutely.
So I think it's quite interesting result.
Yeah. Thank you.
Well, thank you, Jonas, for your presentations, and thank you all the presenters and the speakers on this session. I really enjoyed the time, and we had an interesting discussion. I think the papers will be there for any further discussion. And thank you very much to all of you. Thanks, Isaac, for the support. We are done with the session number 90. Thank you, everybody, for being here.
Thank you, Santiago, for hosting and having us.
Thank you.
Thank you all. Have a nice day.
Bye. Bye.
Bye. Bye.
Isaac, ¿estamos listos?
Todo perfecto. Muchísimas gracias.
Estuvo bien la cosa.
Muy bien, sí. Gracias por el tiempo y demás.
Poca gente en esta.
Sí, fíjate que en la tarde hay un poco de caída en la participación, bueno, en la tarde aquí, pero bueno, la verdad es que bastante interacciones, la gente platicó, hubo discusiones, eso estuvo bastante interesante, la verdad.
¿En esta? Sí,
en esta en particular, sí.
Este estuvo bien, éramos poquitos, entonces la gente ahí preguntaba.
Sí,
bueno,
sí, se mostraron muy interesados. Muchísimas gracias, Santiago, por todo.
Gracias a ti, que estés bien.
Seguro, igualmente, tú también, cuídate mucho y saludos hasta Colombia.
Lo mismo a ti, que estés bien.
Cuídate mucho. Chao.